AP Lab number 7, Purity of Mixtures. So first of all, we didn't have a conductive probe, so we did the best we could with the voltmeter. In an ideal situation, when you graph your data, it should be a linear relationship. Okay, that's what we're looking for. So you had the ability to change your mixtures and how much of each one you're going to have in there, but it should be a linear relationship. So just include your graph on that. That was a manual graph that you did. And the one thing we kind of want to see is that hopefully, depending on your data, we observed and noted that there was a trend that the greater amount, so the greater amount of Na2CO3 in mixture leads to greater conductivity. So that's what we were kind of trying to go for there, okay? And that supports pre-lab question number 3. So that's what that's supposed to do. So let's go on to the next part of the lab. So the next part, you were taking the crucible and you were heating it and trying to keep it between the range of 100 degrees and 851. Okay, hence why we try to use the hot plate. Some of y'all still use the Bunsen burners, yada, yada, yada. So let's just say that I have an example of 1.025 grams of NaHCO3 and 0.990 grams of Na2CO3. So what are some things I need to pull out of it? Okay, so I have a total for this mixture of 2.015 grams. Okay, so let's just say, okay, I've got my mass of my crucible. If I put a cover on there, great, and the mixture. Okay, and then, so before I start with a 30.202 grams. All right, and I know that this weighs 28.187 grams. So this is just some example data, all right? So then I heat it, and after heating, I get 29.937 grams. Okay? So my difference between these two numbers is 0.265. Okay? And it did point out there that you're supposed to weigh it more than once, and the idea is if you weigh it twice and get the same number, then you've thoroughly decomposed the mixture. Okay? So that's why they put in there, weigh it more, do this more than once, right? Okay. So the mass loss, the difference here, we are saying it's because of carbon dioxide being given off. Okay? And that's due to the decomp of NaHCO3, and we saw that in question number 2. Okay? So if I take the moles of CO2 produced, then I get 0.265 grams, and I'm going to take 44.01 grams to 1 mole of CO2, and we're going to get 0.00602 moles of CO2. So you got to do that calculation. All right. So according to the balanced equation for decomposition in NaHCO3, I have 2 moles of NaHCO3 produces 1 mole of CO2. Okay, so thus 0.00602 moles of CO2 came from, we're going to double that number, 0.0120 mole of NaHCO3. Okay, all right. So now I'm going to take that number that I have, 0.0120 moles NaHCO3, And let's convert that over to our grams. Okay, so that's 84.007 grams to 1 mole of NaHCO3. And I'm going to find that I get 1.0081 grams of NaHCO3. Okay, the original mixture contained 1.025 grams. So pretty good, all right? So the theoretical mole, all right, I'm going to do something here because I need myself a little bit more space because I write too big. So let's look at the theoretical part of it. All right. Okay, so there it is. All right. All right. So theoretical. Okay. So if I take 1.025 grams and I divide it by the 84.007 grams to 1 mole of NaHCO3, I'm going to find out that I could produce 0.0122 mole of NaHCO3. This is on theory, okay? So according to the balanced chemical equation for the decomposition of NaHCO3, 2 moles of NaHCO3 produces 1 mole of CO2. So if I have 0.0122 moles of NaHCO3, I should be able to produce 0.00610 moles of CO2. So the theoretical mass of CO2 produced, and we'll do that calculation real quick, 0.00610 mole of CO2. And we got 44.01 grams CO2 to 1 mole CO2 equals, come on, 0.268 grams of CO2. Okay, and that's how we're going to figure that out. You could also do percent error on that too if you wanted to extend that further. So that's a calculation there. So now you also have the gas pressure sensor data, and you had to do it for the 2 runs, and hopefully you had no problem with that. This first figure is going to be the 0.20 grams of Na2CO3 added to 10 milliliters of 0.83 moles of acetic acid, which is commercial white vinegar. The temperature of the reaction was 22.0 degrees or 295.15 K. Okay. Oops. Okay. And the pressure change was 33.16. Okay. Water vapor pressure at 295 K. This is important to know. So my water vapor pressure at 295.15 K equals 2.643 kilopascals. And the volume of the Erlenmeyer flask was 147.0 milliliters. Okay. And we assume automatically that the acetic acid is in excess, and thus is presumed that the entire amount of Na2CO3 is reactive. Okay. So we had our balanced equation that we had earlier. So we have Na2CO3 plus 2C, and we saw this on our pre-lab that we wrote up. Okay, so this is what we're referring back to. I'm going to run out of room here, so you can refer back to your pre-lab. The theoretical amount of CO2 produced is based on the molar amount of Na2CO3. So if I have, if I look at my moles of Na2CO3 and they equal 0.20, sorry, that's wrong. grams, boom. That weighs 105.989 grams to 1 mole. And that equals 9 mole Na2CO3, which means that I produce 0.0019 moles of CO2. Okay, so now we're going to get into our equation. So P equals P total minus P water. And so my P equals 33.16 minus 2.643 kilopascals. Okay, so just taking these two values here, all right, and we're going to get 30.52 kilopascals. So we're just correcting for the water vapor that's present in there. So my volume equals 0.147 liters. R equals 8.31446 liters, kilopascals over K per mole. And my T equals 295.15 K. So to solve for my N, I'm going to rearrange my ideal gas law equation, and I'm going to sub my values in, and we're going to get 30.52 kilopascals times 0.147 liters divided by 8.31446 times 295.15, and we're going to get 0.00183 moles of CO2. Okay, we're going to repeat that with the other one as well. Okay, so similar setup, still 295K. Our delta P on this one is 39.27 kilopascals. The water vapor, again, will be 2.6 because it's based on your temperature, okay, which is still 295.15 K. All right, and the Erlenmeyer flask this time is 151. Okay, we still have our balanced equation. All right, the theoretical amount of CO2 produced based on the molar amount of NaHCO3. So we're going to take that value that we have, it's 0.20 because we weighed out the same amount. And this time we are going to divide it by 84.007 grams to 1 mole. And we're going to get 0.0024 moles of NaHCO3. And based on our equation, that also equals the amount of carbon dioxide. Right? Okay. So now we're back to we got to get our adjustment for our pressure. So we do our pressure total minus our pressure water, which equals 39.27 kilopascals minus that correction that we have, the 2.643, which gives me 36.63 kilopascals. We know that our volume, when we change it over to liters, is 0.151 liters. Our R is still 8.31 liters, kilopascals over moles K. And then temperature is still 295.15 K. When we rearrange to solve for our N, we're going to get 36.63 kilopascals times 0.151 liters divided by 8.314 times 295.15. And when I do this calculation, I get 0.00225 moles of CO2. Okay, so we can see the difference between those two. Additional information, hopefully you can see the different ways of testing for mixtures of sodium bicarbonate and sodium carbonate. They have their advantages, they have their disadvantages, and they have their sources of measurement error. Okay, each one has their problems, and I want you to think about the problems you had for each one. Okay, and that's how you do your lab calculations.